We have another action-packed lecture today. If I am able to get that thing to turn on later, I will try, but otherwise we'll just go ahead and just do with one. So last time we started talking about some of the fundamental concepts or principles behind a programmable computer. And what we're going to do today is actually go through the process of constructing a computer that we can actually program. So we have to have some data representation, and we talked about Boolean values or bits, zeros or ones, and using that representation to do things like arithmetic. We actually had the representation I have here on the slides to represent signed and unsigned integers. So B2U was a way of converting a bit vector into an unsigned int, and B2T was a function for converting a bit vector into a 2's complement signed integer. Remember, all we do is the top bit becomes the signed bit. If the top bit is 1, then it's a negative value, and if the top bit is 0, then it's a 0 or a positive value. And so the top bit just sort of does a shift, an offset kind of thing, where we just subtract that bit's value from everything else that we're doing. So that's what we did for that. We briefly talked about how to construct addition from this, but we're not going to go into much more detail than that. And there's a supplemental document on the Moodle that goes into more information. How do you do subtraction using the adders that we described? And it actually relies very heavily on the fact that to get the 2's complement, like the negative value for a number, we figure out the unsigned representation, we invert the bits, and then we add 1 to it. We can actually use that mechanism to construct an adder-subtractor. And that document that I put online will go through that process of how you do that. So we'll talk about that no more, actually. We won't talk about that anymore, but you can certainly refer to that document if you would like to. Okay, so what do we need to have? What components do we need to actually construct a processor? Because we need several different kinds of components to be able to do this, and so we'll talk about those components today. We need some way of passing signals or groups of signals around. We call them buses. A little bit different than the bus that you might use to go somewhere in the city, but we basically have buses that route signals within the processor. We have this special logic component called an ALU, or the arithmetic and logic unit, and this is a programmable function. You could think of it that way, where you give it control signals to tell it what you want it to do, you give it inputs, and then it computes an output based on your inputs and your control signals. And then finally we have memory, and everybody's familiar with the concept of memory. We just need a way of storing values somewhere so that we can retrieve them later. And that'll actually become critically important as well for our processor to work. So buses, I'm going to try pushing this projector one more time, see if it looks like it'll come on. So yay, we'll get 2 projectors today. So a bus is basically just a collection of wires. It's funny, but it's not really much more complicated than that. If you happen to have done ECS5X, you're probably very familiar with buses. And so we typically have a fixed bit width. 32 bits is going to be the bit width we talk about all term, but obviously most of our computers now do 64 bits, which means they have 64 wires in parallel to carry values between different components in the system. Hey, what? Yeah, I know. It's very exciting. It's quite a relief to me, because this is usually the one I gesticulate at. So, but anyway, buses are used for passing signals from the processor to peripherals, or processor to memory, or even within the processor as well. Okay, that's what we use buses for. And the way we normally draw them on these diagrams is we'll have a line, but we don't want to draw 32 lines or 64 lines or 128 lines would be even worse. So what we do is we draw one line and we put a slash through it to indicate that it has multiple actual lines. It's a bus. And sometimes what you'll see is you'll have a slash, and then underneath the slash you'll write 16 or 32 to say this is how many lines are actually represented by this bus. Okay? So any questions about buses? Easiest thing in the world. We started easy. We'll start getting a little bit harder now. We need a way of controlling whether signals go to one destination or to another destination. And so we have these 2 logic components called multiplexers and demultiplexers, which we can use to do that. And they're very straightforward in their internal operation, which is why we won't really talk about it. If you're curious how a multiplexer would work, then you can look at the document I put on the Moodle this morning. But this would be the way that we represent it. Typically, it's a trapezoid going sideways. And so we have our inputs on the wide side and our output on the narrow side. And we can address which one of those inputs gets passed through to the output. So we have 4 inputs in this example. We need 2 bits to figure out which one we want to choose. And so if we had like the address was set to 00, D0 would come out. If we set it to 01, D1 would come out, and so forth. Pretty straightforward concept. And that allows us to take multiple sources and route one of them to our destination. A demultiplexer is basically the opposite thing. So we have one input and we need to route it to one of n locations. N is usually a power of 2, just for the addressing. So 2 address lines, we can route it to one of 4 destinations. So DN is whatever, address is 00, then it'll come out D0. D1 through D3 will generally be zeros in those situations. So if it's not the chosen output, it'll just be 0. Otherwise, it'll be what other DN is. Okay? Any questions? The reason why we call it a decoder as well is that an alternative way that this is used is to just put a 1 for DN. So always set it to 1. And then you use your address line to figure out which output you want to be 1. That's why we sometimes call it a decoder. But it's a slightly different usage than demultiplexer, even though it's exactly the same logic. Okay? Now we also need a way of doing computations, and that's what our ALU does. And it's this weird trapezoid with a byte out of it. I don't know why they settled on that diagram, but that's what they use. And you can see that we have 2 inputs, A and B. We usually use at least one of them. Like we always will use A in general, but B will be used for 2 argument operations. We have control inputs and so forth. And the control inputs will say, this is the operation I want to perform. Add me up some numbers. I want to subtract I want to subtract B from A, or I want to shift A left by 1 bit, or I want to invert the bits of A. That's what the control inputs will do. And then the output comes out on R. It just comes out through the bottom, and you can see that is also a bus because it's going to be a multi-bit value. And there's also status outputs that tell us some details about our computation that we might care about. And these are the most common status outputs that you might see. The sign flag, or just the topmost bit of R, is it signed or, I shouldn't say is it signed or unsigned. Is it, positive or negative? You have a carryout, which would be your unsigned overflow. Okay? And you'll notice this when we get into IA32, that you have a carry flag, and you use that as your unsigned overflow. Because if your topmost carry bit is 1, then you have an unsigned overflow. Then you also have an overflow flag, which we call it overflow, but really we mean signed overflow. Okay? So that's what that means. And then we have a 0 flag, which will tell us if the answer that we computed is actually all 0 bits, which again is very helpful in certain circumstances. Okay, so that's what our ALU does. And we won't talk about the internals, but the internals basically govern what the control bits are, because the control inputs will turn on and turn off various subunits in the ALU to make it do various computations. It's a really straightforward thing to build, but again, it's sort of just below the material that we'll be covering in this class. It's just a little bit too low level for us. So here's some examples. This is completely contrived. I'm not saying that this has any basis in reality. Like, I don't know if any of you have tinkered with logic, circuits and things like that, but there's the whole 7400 series logic circuits, and I believe there's one of them that's actually a 4-bit ALU, and you can go and look at what its control inputs are. It won't necessarily match exactly this. This is just made up. So you give it 0001, and it'll add A and B together. You give it 0011, and it will subtract B from A, and so forth. So you have these various arithmetic and logical operations you can perform. So yeah, you feed the appropriate control and data signals to our ALU, then we can perform computations. How awesome is that? Any questions? Yeah, and when you have situations where you only have one argument, the B input is basically ignored. You can imagine that inside in the logic, the B signals don't actually affect the result of R at all. So that's the situation if, for example, we just wanted to shift A left by 1 bit, the shoal command. And then B is just completely ignored. It's not actually fed into R at all. Now finally, we need a way storing data, and also, if you think about it, we need a place to store instructions. So this is where memory comes into the picture. And our memory is very simple. You give it an address, and out comes a value. Or you give it an address and a value, and you set some write flag to 1, and it stores that value. Each value is a specific number of bits wide, so we might say our memory is an 8-bit memory, so it can store 8-bit values. Each address corresponds to an 8-bit value. So we'll just draw it this way, very simple. In fact, this is extremely simple. We're taking a lot of liberties. Most memories don't actually work this way, but we have one input for data and one output for data. And we have inputs for addresses, and we have a write flag that says whether or not we want to store D in or whether we just want to produce the current value of the cell on D out. Okay? And yeah, so this is just sort of my aside saying you can construct all of these things from logic, but we're not going to go through how to do that in this class because this is really more of a double E type topic. I remember when I was an undergrad, there was some it was like some like double E11 or double E7 or something where we actually went through all of this stuff. I don't think the class necessarily exists anymore, but you can definitely construct all of these things out of logic gates. I included an extra document if you're curious on the Moodle, but it is not required material or required knowledge, and it shows you some of the simple ways that these things can be built. I think it's neat, but you certainly don't have to know it. So what we're going to do with our components is hook them up this way. Again, we're taking some very simple, or I should say simplifying assumptions here in our design. We have two memories feeding into our ALU. We have somewhere from outer space right now, we have a read address coming in and another read address, a write bit coming in and being fed to both memories. We have a write address being fed in from, to both memories. The ALU output is tied up to the inputs on our memories as well. Why do we have these two memory banks? Well, just to keep things simple. So both the memory banks will be mirror copies of each other. They will always contain the exact same contents at a given address. So address 3 in both memories will be an identical value. And right now we also don't care about the status outputs of our ALU. We don't really care about our computation's status. We just want to store the values of the computations. We'll get to that later. Now that set of inputs into our little assembly here is an instruction. So we have control values. What operation do we want to perform? What addresses are being used for the arguments? Do we want to save the value? And if so, where does it go? All of those inputs form an instruction for our computer. Okay? So if we want to program this thing, we basically need to feed it a sequence of instructions, and we can engineer a larger scale computation using a series of instructions. Okay? Now you can imagine that the operations that this assembly is able to perform is pretty limited at this point. We have whatever control inputs we can pass to the ALU, which we had our little table before, and we'll use that today. We also have what addresses we want to read, what address do we want to write, and so forth. So it's pretty limited. So you can see that if we want to perform a more complicated computation, we're going to have to figure out how to implement it in a series of simple instructions. So first of all, we do need a way of feeding instructions to the computer. So we'll just add another memory. And this is where our instructions will be stored. And our instruction memory also needs to have what address we care about as far as which instruction we're going to feed next. And so we'll do something, again, very simple. We'll just have a little counter, our program counter, which says this is the current instruction that we're operating. And when we complete that instruction, we'll update our program counter to be one more than it was before. That's why I have this little feedback thing with adding 1 to the current program counter value. We're just implementing a little counter. Okay? Are there any questions? There is one thing that is conspicuously absent from this diagram, and that is any notion of a clock. Or in other words, when do we do various things, or when do we update various things? We're not going to talk about that really explicitly, but again, that's a very important question to answer because we want to make sure that the current instruction completes before we update the program counter, And we want to make sure the program counter update completes before we start operating on the new instruction. Otherwise, we don't know that we're going to actually have valid values to operate on. Okay? But we're going to ignore that right now. We're going to just pretend magically somehow everything happens at the right time. Okay, so we already talked about that. Program counter to track current instruction, and we just have it configured to auto-increment throughout the entirety of the instruction memory. Okay, so we have very limited instructions, and typically the operations we want to perform won't already have an instruction that does that operation. We want to do some complicated math thing. Well, probably there's not an instruction that does that complicated math thing, so we're going to have a series of instructions that does it. Since these instructions are very simple, we need to have a way of them to communicate with each other. And so what they do is one instruction will write to a memory location, and then another instruction will be able to read that memory location. So if you happen to have come from CS4, if you've already taken CS4, you probably learned all about the potential dangers of having side effects and how functional programming is really nice because you can construct languages that are side effect free, and that makes it easier to write correct programs. At this level, all you have is side effects. And that's unfortunately part of why it's hard to write these systems or program these systems, because all you have is side effects, and so it can be pretty challenging to make sure that everything operates correctly. So this is the computation we'll implement. And you can see we have this value C we want to compute, and we have these inputs A and B. And so we want to compute B times 2. So we just want to multiply B by 2. We want to subtract that value from A. And then we want to bitwise AND it with this bit mask, 00001111, which basically means we only want the bottom 4 bits of our answer. Okay? There is not an instruction to do this. But there are instructions to do all the parts. So we know that we can compute this, but we will have to figure out the program to do it. Okay, so the first thing we have to do is figure out where are our inputs going to be available for our program, and where should the output be made available so that whatever is turning the crank on the computer, they'll know where the answer is going to pop out. So we have these inputs, A and B. What other inputs might we have? Do we know that 00001111 is already stored somewhere in our computer? We don't. So we also have to make sure that our program includes the constants that we need. And 00001111, I should just say 15 because that's its value in base 10. We need to make sure that that value is available somewhere. So we need to have a location for that as well. And this sort of gives us a little hint as to how real programs, when we write C programs or we write Java programs or Python programs, when you have constants in your program and you compile it, now you don't compile Python, but you compile your program, those constants also have to get stored in the program so that when it executes, the processor has access to the constants that you want to use as well. Same thing here. So we have to make sure our mask is stored somewhere. And our output is C. That one's really easy. The context for our processor, just to give us some ideas, is that our memory is going to be very simple. Only 8 locations, which means we only need 3 bits to access any particular memory address. And our data values are all 8 bits wide. So when we encode the location of A or we encode the location of C, we'll need 3 bits to do it, because we'll need to store a value between 0 and 7. So here is just what I chose. Okay? Again, why did I choose location 4 for the constant? It just seemed like a good idea. It's a convention. It's not really like there is one true answer. Now, it is kind of nice to have the inputs be at the top of the memory and the output to be at the bottom of the memory, so I suppose there's a little bit more rationalization for that. But really, when we're choosing these locations, we just kind of choose whatever seems best to us at the time. So these are the locations that we chose. And so now we need to figure out what series of instructions will encode our computation. And we already kind of described this in a little bit of detail. What's the first thing that we have to do? Can we do the bitwise AND first? No, that doesn't make any sense, right? Because we don't have those values all yet. So we have to do the 2b first. And then after that, we can subtract whatever that is from a. And then finally, we can do our bitwise AND, and we'll have our answer. So we need to know the processor's operations, because we will eventually need to write these little zeros and ones into our program. And so the steps will be something like this. We need to perform 2b first, and we can implement it in a couple of different ways. Note that I have it here as b plus b. What's another way that we could do 2b? Yeah, awesome. You people are awesome. So we could also shift b left by 1 bit, and that would be the same as multiplying it by 2. If you're not convinced of that, you can go through our little B2U and B2T things, and you'll see that that works. It's kind of nice. A lot of processors, I shouldn't say processors, because let me see the right way of explaining this. A lot of compilers will actually implement multiplication by powers of 2 or division by powers of 2 as shifting left and shifting right, because it allows the processor to be used more efficiently. Typically, shift operations are much faster than arithmetic operations. And so if you happen to be working with powers of 2 and the compiler can figure that out, then it will use that to do it very efficiently. But we're going to just use b plus b because our processor sucks anyway. Like, every part of it sucks. It's not able to do anything fast. Okay, then we'll subtract that result, 2b, from a using our sub instruction. And then finally, we'll use our AND instruction. Where is it? AND, 1000. We'll use that to bitwise AND it with our bit mask. Okay? So you can see already, our program is going to have 3 instructions. We have a really complicated program, right? You'll have much more interesting programs besides this. Division turns out to be quite fun to implement, I think. So, but again, you really only need to do this whole 0, 1 thing once. And then you're like sworn off of it forever. So anyway, step 3. So you need to assign locations to these intermediate values. So again, why did I choose these locations? Because they were available. Okay? You probably could take some of these things and write them back to the location that it was already at, just to be more efficient, but we don't care. We just want to go ahead and do the simple thing. So b plus b will be stored in location 2. And then when we compute a minus that, then we'll compute that into location 3. And then the result of the bitwise AND, we can just go ahead and stuff into location 7, because that's our final answer anyway. We can just go ahead and stuff it there. Now we get to do this into instructions, and this is where it gets kind of tedious, because it's really easy to write a 1 where you meant a 0 or a 0 where you meant a 1. And your program will do something different, and it's not easy to understand why it didn't work. So this is the form of our instructions. We have the operation code, 4 bits, read address, 3 bits each, write bit, and then write address, also 3 bits. We also need our memory layout and the operation code so that we can actually code this all up. Oh man, aren't you glad you don't have to do this in real life very much? Okay, so writing our program. So the first thing to do is to compute 2b. We're adding b to itself, so we have 0001. We have address 1 twice, and we store that into address 2. So yeah, slot 2 will be 2b. So we do something like this. No bugs so far? Slot 3 is going to be a minus 2b, so we use the subtract opcode, so 0011, and then we need to put a and 2b into those, so addresses 0 and 2, and we'll store that into address 3. So again, you can see address 0, 000, address 2, 010, and address 3, 011. And then slot 7 is going to be our slot 3 value ANDed with slot 4, and then we just store it into slot 7. So AND is 1000, so we have 1000 as our opcode, address 3, address 4, and address 7. Sorry, I've looked at this program quite a few years by now, so it's pretty easy for me to read. I don't know if it's easy or hard for you to read. But anyway, that is the series of instructions that we need to drive our little computer. Any questions? Okay. Now we're going to pretend that our processor exists. We're going to do employ what we usually call slideware. We're going to emulate all of this on the slides, and so of course it will operate perfectly. But what we need to do to run our program on our processor is somehow set our instruction memory to contain that program. we need to figure out what our initial data values are, so we need to somehow load that into our data memory, and we need to reset our program counter to 0. And then we basically just go through the series of instructions. The current instruction is read out, makes the ALU do its thing, write the values back, and then the program counter goes up by 1. So we go to the next instruction, and we rinse and repeat. We do the same thing over again. And then instructions are able to read previous instructions results by looking in the memory. Okay? So this is going to be all of the state of our computer that we need to think about. Just as a historical aside, again, we should be really happy and glad that we have keyboards and monitors and disks and things like that so that we can actually do this. Because some of the earlier computers that people would use, they'd have a bank of 8 switches. And what you would do is push some button to say, I want to load a program, and the computer would go into a mode where you could set those switches and then push another button. And you'd set the switches to the operation you wanted to perform, push a button, it would store that value into memory, and then go to the next address. And then you'd set the switches for the next value. Push the button, and it would go to the next address. And that is how you would load your programs. And if you got it wrong, you were screwed. That's all you basically had. So it's really nice that we can do this so easily now. We talk about some of those interesting historical things in CS124. It's quite fascinating. Okay, so here's our little computer, the way that we've designed it. We have our instruction memory that we designed our program, and we have our data memory. Now you'll notice that some of these slots, we have no idea what the values are, and we don't care because we're writing to them. So we really don't care what the initial value is. And again, you'll notice this a lot in C programming, that if you create a variable and you happen to look at it before you set it, it may have other stuff in it, but we don't care because we should be only writing to stuff first and then reading it. Okay, so this is our data memory, and our program counter is currently 0. So the first instruction gets executed. Our inputs feed down from instruction memory into the ALU, say, hey, I want you to add me numbers. And the numbers I want you to add are B and B. 001 and 001. And I want you to store that value back into address 2, 010. And so that feeds back into the DN, and the right addresses are set and so forth. So again, you can already see there's multiple steps going on in this instruction. We're kind of skirting over that detail of, well, when do things happen? Okay, just pretend it all happens at the right time. So that happens, then we update our program counter to the next value. Now we execute the next instruction, and it computes A minus 2B using the 2B that we just stored. And let me see. Yeah, so we go ahead and store that into slot 3, 011. So again, that thing happens, and we update our program counter again. And then we AND that result, A minus 2B, with our bit mask, and we store that into slot 7. So that's, yeah, so address 3, address 4, and 7, and that was our bitwise AND opcode. Okay? So that's basically it. That's how our processor runs. Pretty neat. We just implemented a computation that was more complicated than what our processor was really capable of doing by having a sequence of instructions and communicating these values through various memory addresses. So this is a programmable computer. You could use it to compute things. Okay, yay. This is like the rah-rah moment. Wow, we did something awesome. We programmed us a computer. So we can implement various computations, like it says here. This is the series of steps that we went through, and this is going to become important because you will have to do this when you are given a program to implement and said you have to do this in machine code or you have to do this in assembly language. So this is the series of steps we kind of went through. We assign memory locations to our inputs and outputs. We decompose this computation into what the processor is actually capable of doing. That's really kind of the hard part of doing this whole thing. We assign memory locations for any intermediate values that we needed to store. And then we encoded our sequence of instructions using our opcode table, our addresses, and so forth, and our instruction format. We just went ahead and coded that up. And then we can feed this series of instructions into our processor, and that will allow us to perform our computation in multiple steps. Okay? So this is basically all we need to do. Any questions at this point? So this was our program, and you can see that this is very difficult for a human being to have to deal with. This was what people had to do at the very beginning when computers were first created, because we didn't have all the nice stuff like higher level languages and compilers and so forth. This is called machine code because it is what the processor actually deals with. This is what the processor understands. So you might have a series of binary values, or you might have a series of hexadecimal values, but it's all just numbers because that's what drives the processor. And it is very difficult to read and write. And so again, we started adding abstractions to the hierarchy, and the next step was assembly language. Assembly language and machine code are different. Assembly language is a little bit easier for human beings to deal with. So we might have something, I have an example of how we might write the same program in assembly language. Again, this is contrived, it's not a real assembly language. So I want to add the values R1 and R1 into slot R2. I want to subtract R2 from R0 and store the result into R3. Notice we don't have the opcodes, we don't have the write bit, we don't have all of those things. They're inferred by the assembler from the instruction being performed. And the assembler would take these instructions and generate bits that the processor will be able to deal with. But it allows the human being to write code at a higher level so that it's easier for humans to understand. Okay? So that's where assembly language really fits into the picture. And you can imagine you can just extend this abstraction hierarchy on and on. When we compile a C program, it generates assembly code. And then the assembly code is fed through an assembler, which generates machine code. So you have the same series of steps. We leverage our abstraction hierarchy. Okay? Now, what we need to do next is talk about C logical and bitwise operations, because you'll actually need these for the first assignment. And you probably are familiar with some of this stuff, but there's various other operations you can perform in C to manipulate bits as well. So we have integers that we use to represent Boolean values. 0 means false, and anything else is true. If it's 1, 64, -1, all of those things would be considered true in C. And we have these logical Boolean operations. So logical AND, 2 ampersands, logical OR, 2 pipes. That's what we call that character, is a pipe. And logical NOT, exclamation point, or colloquially it's usually called bang. So bang A is not A. I usually just say not A. That's easier. And the result of these things, you can see it's 1 if it's true, or it's 0 if it's false. And the logical operations are short-circuiting or lazy operations. Because once they reach a certain point where they know the answer, then they stop evaluating the rest of the arguments. So if, for example, A double ampersand B is the expression we're evaluating, and A is false, I know there's no point in considering anything else. Because false and anything is always false. Same thing with OR. If A was true, then I wouldn't evaluate anything else, because true or anything else is always true. There's no reason to consider everything else. And we can take advantage of this when we write programs to say, like, is this pointer not null, and also some other things? Because if the pointer is null, I don't want to perform the other things. I might generate a seg fault. So I just say if the pointer is not null and other things, and the pointer ends up being null, I don't even evaluate those things. Okay? So that's how the short-circuiting operations work. Now these are all logical. We call them logical operations because they treat integers in the way described above. 0 is false and any non-zero value is true. There are also bitwise operations, which typically are a single character. So A single ampersand B, and you end up with a bitwise AND instead. And here, individual bits are the things that are operated on. So we have A, in this case, is 20, and B is 50, and there are the bit patterns for those. A, bitwise AND B will produce a 1 in the result where both inputs have 1. A single pipe B is bitwise OR, and it'll generate a 1 where any of the inputs have 1 for that bit. Tilde is bitwise negation, or 1's complement inversion is what we call it. Okay, but we just invert each bit in the byte. And then A caret B is bitwise exclusive OR, which is kind of a special operation. You don't see it too often, but exclusive OR can be used in various ways. Specifically, it's frequently used to toggle particular bits. I'll have a slide where we talk about some of those things. Maybe so I think it might be the next slide. Unfortunately, there's no way to write out values using just zeros and ones in C. So if you want to specify some literal value that corresponds to a particular bit vector, then typically we have to do it using hexadecimal, not binary. Okay? Who here has worked with hexadecimal before? Show of hands. Okay, so a lot of you have seen hexadecimal. That'll help. Hexadecimal is basically like our normal representation of numbers if you also had 6 more digits that you could use to represent numbers. So it's base 16 instead of base 10. You can see there's a lot of different bases that we work with in computer programming. There's base 2, base 16, and a lot of times, for historical reasons, you'll see base 8, also known as octal. But hopefully you won't run into that very much in CS24. So base 16 numbers, the additional digits that we need 6 more digits. We usually write them as A through F, and it doesn't matter what the case is, but if you choose a particular case, stick with it for all of your programming. Because that's another coding style thing. You should use all lowercase a through F or all uppercase a through F when you write hexadecimal numbers, just to keep things clean looking. So you can see that if you have just A by itself, that means 10 in base 10. F by itself would mean 15 in base 10. Okay, and the way that you convert back and forth between hexadecimal and decimal, or hexadecimal and base 2, pretty straightforward. We won't talk about it here. You can either ask me or a TA how to do that if you're uncertain of how that might work. Okay, so like I have here, 0x0f is a hexadecimal literal in C. You could also have a lowercase f. And you can see that each digit of the hexadecimal value corresponds to 4 bits. Because base 16, you can imagine each digit is going to be represented by 4 bits. And so it's a pretty easy way of translating between base 2 and base 16. You just sort of memorize what the different hexadecimal digits correspond to in your bits, and then it becomes really easy to translate back and forth. So 0x0f would be 00001111, really easy. 03C7, oh no, what is that? Well, you have 4 digits, so you know you're going to have 4 times 4, or 16 bits. And you can go through and just look at each digit in sequence. Well, 0 is 0000, that's an easy one. 3 is 0011. Okay, the ones column is 1, and the twos column is 1, so 1 plus 2 is 3. Then C, you have right there, what is that? That's 12, I believe. And then 7, 0111. Okay, so that's the easy way to just translate back and forth between base 2 and hexadecimal. Okay, so we can use bitwise AND, like I said, to mask out. We call it masking out because it's like having a mask. I only want to look at this part. So 0F, that'll mask out the top 4 bits and only keep the bottom 4 bits. So that would be a way of retrieving only the low nibble of A, if you had multiple values stored in that variable. Bitwise OR, to set specific bits. So if I take A and I bitwise OR it with 28 hexadecimal, then you go ahead and set those bits. It's kind of an interesting thing, just as an aside. Where would you bitwise OR things? It turns out that if you want to convert from lowercase characters to uppercase characters in US ASCII, you can just set a bit, and your uppercase A will turn into a lowercase a, or your uppercase Q or your lowercase q will turn into an uppercase q. Same thing if you want to convert it from lowercase to uppercase, you can mask out a particular bit, and it'll change it from lowercase to uppercase. Random useless tricks. Well, I guess they're useful if you need to do that kind of stuff. But anyway, A equals A, bitwise OR to 28. That'll set bits 3 and 5, because you can look at what that bit vector would be in base 2. So 2 would be 0010, and 8 would be 1000. And all the other bits of A will remain unchanged. Okay. And then finally, bitwise XOR would be used to toggle specific bits. So again, if you did this with a caret instead of a pipe, sounds weird to describe it that way, but if you did this with a caret instead of a pipe, then you would end up with toggling bits 3 and 5. You know, if you think the existing value, or the existing bit of A is 1, and the bit in the XOR mask is 1, then 1 XOR 1 is 0. If it's 0, then you have 1 XOR 0 is 1. So it toggles that bit. Okay? Any questions? Why might you need to do this kind of thing? Well, thankfully you don't generally in CS24. But if you take like a 5X class or some other digital systems programming class, this is where you kind of need to do things, because typically on hardware, you'll have to set specific bits or clear specific bits to get the hardware to do specific things. If you take the OS class, you'll have to do it again because operating systems obviously interact with hardware. So you have to set and clear various bits. And so these bitwise operations become very, very helpful. So that's why it's good to know about them. Okay, bit shifting operations. So this is the other thing we can do in C. We have shift left, which some of you already recognized. You can use this to multiply by 2. The new bits on the right are 0. It wouldn't make sense to set them to something else, but the new bits on the right will be 0. And it's identical to multiplying by 2 to the number of bits that you shift. So if I have A is 42, and I want to shift it left by 1 bit, then I'll end up with 84. If I wanted to shift it left by 2 bits, then I would end up with 168, I believe, and so forth. So you can use this to implement multiplication by powers of 2. You can shift bits right as well. So A greater than N. So here's a question though. I shift right. I said on shift left, when I shift left, the new bits that I'm adding to the right side of the value are 0. What should they be when I shift left, or when I shift right? What should the leftmost bits be? Should they always be 0? I'm seeing a few shaking heads. Why would that be a bad idea? Yeah. Yeah, if I have a signed value, remember that topmost bit is really important. That tells me that it's a negative number, or it tells me that it's a non-negative number. So if I shift right, and it happens to be a negative number, then I need to be a little bit more careful about what I do with that top bit. Now if I'm doing unsigned shifting, then I want to just put zeros in. But if I'm doing sign shifting, then I want to retain that topmost bit to preserve the sign. So like I say here, A is minus 24. The 2's complement value of that would be the bit vector I have here, 1110, 1000. If I want to shift that right by 1 bit, then I should end up with minus 12. And the only way that I can do that is if I preserve that topmost bit. Okay? So you can see that in the case of sign shifting, I need to just retain the topmost bit, whatever its previous value was, keep it. So we distinguish between these two kinds of right shift operations. You have arithmetic shift right, and you have logical or bitwise shift right. Okay? And the arithmetic shift right preserves the sign, and the logical shift right, or the bitwise shift right, doesn't care. It doesn't preserve the sign. There are languages that make a distinction here. Java is a great example where the typical shift right is always signed because Java's integer types, except for char, are all signed. Okay, char is the only unsigned type in Java. IA32 assembly actually also makes a distinction as well. You have SAR and you have SURE. And SAR is the A stands for arithmetic. And the SURE just means a logical shift right. So SAR preserves the sign and SURE does not. Now C, unfortunately, doesn't make any distinction. You have to think when you write C code. You have to do the thinking for C on this particular point. Because it will just infer from the type whether or not it's doing signed or unsigned shifting. Because you can have char, you can have unsigned char, you can have int, you can have unsigned int. So char A is minus 24. That's a signed character. And if you shift it right by 1 bit, then you'll get minus 12. Or you can cast it and say, you know what, I actually want an unsigned char. And then when you shift it right, it won't preserve the signed bit, and you'll end up with 116, because it will put a 0 in the topmost value instead of a 1. Okay, everybody got that? So that's the detail there. Let's see, yeah, so we can use bit shifts and masks to extract values. So A greater than 4. So notice I'm shifting A right by 4 bits. Presume that A is an 8-bit value, so I'm shifting it right by 4 bits. Now I only have the 4 bits in A that were the top nibble, and then I bitwise and that with 0F. Okay, so I can certainly do something like that to get the high nibble of A. And here's a question. Does it matter if A is a signed or unsigned char in this bit of code? Anybody want to? You have like a 50% chance of being right. Unless you always guess no and you're like, well, I guess you still have a 50. No? It doesn't matter. Why not?
Because when you shift right, you can get 1, but those are going to get messed out
Yeah, it doesn't really matter. If A was an unsigned char, we'd get zeros at the top. If A was a signed char, then we'd get ones at the top, but we throw out those top bits when we do our bitwise AND. We bitwise AND it with 0f, and that throws away all the bits above the low nibble. Okay? So hopefully this will help you start thinking about how this kind of code works. Okay, this is our processor's instruction set. Can we implement multiplication? Well, certainly not by calling the non-existent mul instruction, right? We don't have a mul instruction, so we can't do multiplication. But that's okay, because we do have addition, and we do have bit shifting. And it turns out that you can actually multiply two w-bit bit vectors with this simple algorithm. Notice we're just taking this, we're looking at the b value, and we multiply it by 2 to the I, and we just look at a sub I, that bit in A, to decide whether or not we need to include that component when we're performing our summation that's equivalent to our multiplication. And this algorithm is a very simple way of implementing that. Notice we just keep shifting b left by 1 bit to do the b to the b times 2 to the I. So we keep shifting it left by a bit because we're doing them in sequence. And we just look at the low bit in A. Okay, that's fine. We can do that, and we can decide if we need to add that into the product. Okay? So we know we can implement multiplication. Right? We have add, we have shift right, we have shift left, we have bitwise AND. We look okay. But this is the problem. Are we actually able to implement this program? I'm seeing some no's. Why can't we do it? We don't have any jump instructions. We have a few other things that we need as well. Like we definitely don't have jump, so we can't do loops. Yeah. Yeah, we don't have any way to compare things together. Conditional operations is what they're called. So, for example, when we say A bitwise ANDed with 1, we have no way at all of telling, well, what was the result of that? Let's do something or not do something based on the result of that A bitwise ANDed with 1. We have no way of doing that yet. So you can see that our processor is just too simple at this point. We need to add some more facilities to it before we can actually start implementing crazy, complicated things like loops and if statements. And if you look at our design, it's really obvious, because where does the instruction memory get its addresses? Well, we have this program counter, and we just keep incrementing it. So if you look at this, you can say, oh, okay, well, I need to make my program counter logic more complicated. I need to be able to feed addresses into it sometimes if I want to jump somewhere. And if I want to do conditional operations, then I need to look at the status outputs from my ALU. I need to start looking at this stuff if I'm going to be able to implement these more complex programs. Okay, so like I say here, you need to be able to update the program counter field, and we also need to be able to look at status values. Now you might say, well, that seems dumb. Every processor should have conditional operations and jumping. It turns out that not every kind of processor needs it. GPUs are a very notable example of where the processor is actually not able to jump in your program. It has ways of faking it, which is really cool. It's a little bit beyond the scope of what we're going to talk about here in CS24, but when you translate a GPU program, it unrolls loops into a series of operations so that it actually is able to eliminate the loops. And it's able to do conditional moves and conditional sets and so forth, so that it doesn't need to actually update the program counter. So the GPU is able to have very fast, simple processors because it's processing a huge amount of data. You want it to go as fast as possible. So it's kind of interesting. Not every processor actually requires that you have anything more complicated than this, or much more complicated. Okay? But we do need it if we want to write general purpose computations. But still, we accomplished a lot today, and that's pretty neat. We have this simple programmable computer now. We looked at the components that we needed. We figured out how to put them together. We figured out how to set up instructions that communicate to each other. We figured out how to turn the crank to go ahead and get a result out. The instructions communicate by reading and writing values. But we still have a lot of limitations, and that's what we're going to start addressing next time. How do we actually make a processor that's able to do more complex things? We're going to start with loops, and we'll go from there. And we also have very limited memory addressing in our computer as well, so that's something else that we need to fix. Okay? So we'll go ahead and start talking about those things on Friday. See you then.